Hello, and welcome to my video on volume of a solid revolution by disk method. So a solid revolution is obtained by rotating a region about an axis. We use the terms revolve and rotate interchangeably. Here's some examples. If I took this triangular region and I spun it around the y-axis, I would get this cone-shaped object. And if you look at the cross sections going this way, so the cross sections are circles. So circle, cross section, perpendicular to the y-axis, perpendicular to the axis of revolution. Okay. If we look at the next one, which is a semicircle, if we rotate that around the x-axis, imagine spinning that thing around the x-axis, we would get this sphere. Okay, and the cross sections going this way are also circles. So circular, let's try that again. Circular cross section perpendicular to the x-axis, which was the axis of revolution. Now the cross sections going perpendicular to the y-axis also happen to be circles, but I'm more focused on the cross sections that are perpendicular to the x-axis, our axis of revolution. Okay, so this is what we're doing in this section. We're basically taking bounded regions. We're going to rotate them for now only around the x-axis or the y-axis. We're going to create a three-dimensional shape, and we're trying to calculate the volume of that shape. Now, I drew the cross sections in for a reason. These cross sections are really, really important in how we do our calculation. So let's discuss that. So if we take f of x, and we take this region between a and b, and we spin this region around the x-axis, it's going to create this three-dimensional object you see on the right. So this is our 3D object. Now, the most important part is not really the three-dimensional shape necessarily. It's actually understanding what the cross-section is. So the cross-section is a circle. So cross-section is a circle. This is critical to our calculation for the volume. Because, if you think back to geometry, if I was able to take every single cross-section possible, if I add them all up, it would give me the volume of this shape right here. That's essentially like base area times the height. If we think of this part right here as like our base, and if we multiply it by the height, we find the volume. The problem is these circular cross-sections are constantly changing based on the function. So right here, this, for my circle, is my radius. And you'll notice that your radius is actually the function value, right? So each cross-section, the radius is f of x. So f of x equals the radius of each cross-section. Now, the volume, a very simple rudimentary calculation for volume using integration, will be the integral from a to b of the area of the cross-section dx, because we're going around the x-axis, okay, and we're going from, as it says here, a to b. So that's the basic concept. If I could figure out what the area of one cross-section is, that calculation, whatever that is, if I integrate that from a to b, I'm going to get the volume of my object. Now, we know that a circle, the area equals pi r squared. So we keep going. So a to b of pi r squared dx, because the cross-section, again, is a circle. But in this case, what's r? Now, r is not constant, okay? Depending on where I end up, so like right now, this is r from here to here, because if I spun that thing around, it would create this circle, right? But over here, r is different, and right here, r is different, and right here, r is different. My r is constantly changing. So my r is based on the function itself. Remember how I said r equals f of x? That's why, because r is constantly changing. So we're going to integrate from a to b pi times f of x squared dx. And typically we put the pi out front, not that you have to, but we usually move the pi out front. There we go. That's how we calculate the volume of a solid of revolution for spinning around the x-axis, okay? Now, what about if we spin this thing around the y-axis? It's the same thing, except everything must be in terms of y. So my volume is pi integral, I'm going to maybe use c and d as it says here, and my radius is not f of x, it's f of y squared dy. Exact same calculation, okay? So you'll notice we call this a disk technique because the cross-section, yes, it is a circle, we call it disk, but the cross-section is circular and it's fully filled in. There's no holes or gaps or anything like that. So if I just take the area of one circle, do that an infinite number of times, add them all up, I get the volume. And hopefully that point is sunk in a little bit, but it's still a challenging thing to kind of focus on. So here we go. We want to find the volume of the solid generated by revolving y about this x-axis, okay? So we have square root of x is our function, that's this right here. That's our function. And we're going from 0 to 4, and we're spinning it around the x-axis. Now, you could think of r, and this is going to help us in our next video, as top minus bottom. Okay, so if I did top minus bottom, the top is root x, the bottom is just 0. This is y equals 0, that function, right? So 0. So I just get root x. In the future, that top minus bottom calculation is going to change, and our r is not going to be quite as simple. So you'll notice there's a three-dimensional picture here, but right there, that's r, and it's actually just the square root of x. So we integrate from 0 to 4, x value to x value, put a pi out front because we're doing volume, and we're finding the cross-section is circles. We want the area of a circle. So r, this is going to equal r, our radius. This is going to be root x squared dx. So we get pi integral from 0 to 4 of x dx. We have pi times the quantity 1/2 x squared from 0 to 4. So that would be pi times, let's see, 16 times 1/2 is 8 minus 0. So this is going to have a volume of 8 pi. Cube units, but we don't have to put any units because there's none given really. So that would be our answer for that one, okay? Okay, so let's take a look at question number 2 now. I'm actually going to make a couple adjustments here. I actually want to keep or change this function. Let's make this y equals 1/3 x squared. And we're actually missing a bound. We should say and the x-axis it's bounded by. Okay, so let's go ahead and sketch this out. See what we got going on. So we have 1, 2, 3, 1, 2, 3. That's my -3 and my 3. So those boundaries are these vertical lines. Let me draw this a little better. So we got a line there. We have a line there. Okay, we also know the x-axis is one of our boundaries, so I'll go ahead and highlight that, x-axis. And then we have this quadratic that opens up. We don't need to be super precise, to be honest. We just got to draw. I'm going to go ahead and draw this a little dramatic, I guess, but there we go. Okay, we're trying to basically take these two regions, okay, that's our bounded space, and we're going to spin it around the x-axis. So if you can visualize what's going to happen, you're almost going to have this kind of like double spinning top. Okay, almost like bow tie type shape, whatever you want to call it. This is what it would look like in 3 dimensions. And each cross-section of this object would be a circle, right? Such that this is your radius. Well, this part right here is r, or this part right here is r. So what is that? That is the function itself, right? That is 1/3 x cubed, or we could call it f of x, whatever we want to call that. Okay, so the function itself, because a function represents the distance from the x-axis to the curve. We could also think about it as top minus bottom. So you could think of it as 1/3 x, it's supposed to be x squared. 1/3 x squared minus 0, because the bottom is y equals 0. Same concept, top minus bottom. And that will be very useful when we do washer type problems. So I actually have a little image creator here. So there's our function. Right now we're looking at it in 2 dimensions. So I'm going to rotate my axis. The z-axis is our 3rd dimension. It's kind of coming upward now. And if we maybe make it look like this, and we start our animation, we can see what happens when we rotate that shaded region around the x-axis. The red axis is the x-axis. So if we spin that around, look at what happens. We get this really interesting looking shape. Let's say we maybe stop it right about there. And let's go ahead and fill this in. And you can see what that thing looks like in 3 dimensions. Now, this thing looks hollow based on how the computer drew it. Like, it looks hollow right here. But this is actually solid because this shaded region is going to sweep out this whole solid shape. All right, pretty interesting looking object. And we can, using calculus, we can calculate the volume of that object. So we know that the volume is pi from A to B of, I'll call it r of x squared, whatever that radius is. And in this case, that radius is our function, right? 1/3 x squared. And we're going from -3, x value to x value. So -3 to 3 of 1/3 x squared squared, because we have to square it, it's r squared. Again, how does that formula work? Area of a circle is pi r squared. And if we wanted to save ourselves some work, we could use symmetry. Right, this shape is symmetric, so I could just go 2 pi integral from 0 to 3 maybe of, let's say, 1/9 x to the 4th. I went ahead and squared everything. Okay, and then we would find the antiderivative, apply the FTC, finish the problem, but we'll go ahead and just leave it at that. All right, keep this thing moving. Okay, number 3. Now, there's an adjustment here. You will notice that we are rotating about the y-axis. Very important. If we're spinning around the y-axis, everything must be in terms of y. Very important. Anytime we spin around a vertical axis, we must have everything in terms of the vertical component, which is the y value. So we would have normally our volume is pi integral, I'm going to use c and d now, so c to d of r of y squared dy. Okay, you'll notice our function is this, xy equals 2. Well, we want to solve that for x. So we get 2 over y, which is the same as 2y to the -1. And you can see that right here in our image. Okay, now, just like for a function with respect to x, when you have a function with respect to y, it represents this distance right here, from the y-axis to the function, from the y-axis to the function, from the y-axis to the function. These are our r's. That's what becomes the radius of all of these cross sections right here. Okay? Again, pretty interesting shape. We're not too concerned about what the shape looks like. We just got to be able to calculate the volume. And we want to go from y value to y value. So this value to this value. All right, so we've got the volume equals pi integral from 1 to 4 of 2y to the -1 squared dy. So we're going to have, I'll go ahead and work out most of this one. So we're going to have pi, my antiderivative is going to be, actually, you know what, I should go ahead and simplify my integral first a little bit to help you out. So this is 4y to the -2. Remember, power to a power, you multiply. So now my antiderivative, I'm going to have a pi out front. We're going to add 1 to the exponent. So it's y to the -1, multiplied by the reciprocal. So I get -4 from 1 to 4. Apply the FTC, so pi. If I plug in -4, I'm going to get -4 over 4, because you're going to have 4 to the -1, which is 1 over 4, minus -4 times 1, so just -4. So we get pi, and we're going to have -1 plus 4, which is 3, and we get 3 pi. That would be the volume of that three-dimensional shape. Okay, so the key here is when you're spinning around a vertical axis, you'll notice that our function is in terms of y, and our limits of integration are also in terms of y. All right, so that's actually going to be it for this video. We will save question number 4 for class, talk about it together. So thank you very much for watching. If you have any questions, please let me know.